Okay, so here we are at week 9, and this week we're studying acoustic characteristics of speech sounds. This is finally the last week of the acoustics marathon. So this week we're going to apply what we've been learning over the past 3 weeks to actual speech sounds, all speech sounds. We learned to distinguish between different classes of sounds and also to distinguish between sounds within a class. As usual, this video will review last week, preview this week's material, and note some important stuff coming up this week. So, last week we looked at source filter theory and ended with a big tie-in to vowels, so that should produce a nice bridge, or provide a nice bridge to what we cover this week. You also submitted the second of 3 transcription assignments. The marks for that one will be out shortly, and the third transcription assignment should be available this week. Okay, speaking of this week. So this week we're looking at how to distinguish speech sounds based on their acoustic characteristics. And here's where I really start to encourage you to play around in Pratt. Record yourself making different sounds, see what you can see, try it. It's the best way to get on top of this week's material. The chapter starts with a discussion of vowels. As we saw last week, this is all about resonances. In fact, with very few exceptions, the first 2 formants, that is, the first 2 resonances, can tell us most of what we want to know about vowels. The 3 main patterns to keep in mind here are that vowel height is inversely correlated with F1 frequency. So a more open articulation produces a higher F1 frequency, and a more close articulation produces a lower F2 frequency. Frontness, vowel frontness, corresponds to the distance between F1 and F2. Front vowels have a big gap between those 2 formants, back vowels have a smaller gap. Rounding for vowels causes a drop in the frequency of all formants. Now, the magnitude of these effects and what counts as a high or a low value for a formant, it varies from person to person. If you choose the vowel acoustics option for this second lab assignment, you'll get a chance to explore that with your own vowels. The textbook also touches on vowel length and on diphthongs. Basically, vowel length corresponds to how much duration you maintain a vowel for, and a diphthong is moving from one vowel to essentially another vowel position. So you see a slowish transition between the formants for one section and for the other section of the diphthong. Next, we look at consonants, starting with the approximants. Now, from an articulatory standpoint, approximants get their name from the approximate or slight closure of the vocal tract. Acoustically, approximants they look approximately like vowels. They have similar formant structures, slightly less acoustic energy, generally shorter duration. So approximants like the labial velar, the palatal, the labial palatal, the velar, they'll have formant patterns that can be compared to those of certain vowels. On the other hand, the coronal approximants, the alveolar and retroflex ones, not coincidentally the ones with the R shape in their the shape of their IPA characters, they have this characteristic dip in F3. Next we go on to fricatives, and these are primarily distinguished from other classes of sounds by noise, that random hissing sound energy that's created by turbulence of the kind of constriction we get with fricatives. The energy distribution of that noise can help to identify what fricative we're dealing with. And I'm not going to bother with the formulas from the textbook here. They're good to have around, but let's focus on the general ideas. The main acoustic cues to distinguish different fricatives are: where is the energy located? Do we have more high frequency energy, more low frequency energy, or is it diffuse across the whole spectrum? How much energy? Is it overall a lot of noise energy? That's sibilance. Or not much? Non-sibilance. And of course, you can also look for voicing along the way. If there's that characteristic repeated pulse of voicing, then you know it's a voiced fricative. If not, then it's voiceless. Next, we look at plosives, and here's where the idea of silence as a wave, as a type of wave, comes in handy. All plosives have a release burst. Acoustically, that's an impulse in the waveform, and they tend to have a bit of silence or relative silence immediately preceding that. When there's a vowel next to a plosive, we get formant transitions, and these mark how the tongue is moving from the vowel position to the consonant position. So these transitions tend to be different for different consonant places of articulation, different places that the tongue is moving to. tongue and other articulators, I should say. As with fricatives, we can look for voicing in the acoustics to distinguish voiced from voiceless plosives, and pay attention to the timing of that voicing too to identify aspiration as well. After plosives, we see nasals, and here we get a new acoustic concept. That's the antiformants. Basically, this is a branching in the tube that bleeds off some of the acoustic energy. So you get a dip rather than a peak, an antiformant. After nasals, we get the lateral approximants, which are like approximants, but they also have a split in the channel. This time it's a lateral split, and that branching does the same thing. It creates an antiformant by dividing up the acoustic energy. And the discussion of consonants ends with affricates, which are pretty easy after all the rest, because as you already know, an affricate is just a stop fricative sequence, right? Okay, so from the time of the earliest oscillograms, acoustic phoneticians have been looking for ways to read the sound off of visual representations, waveforms, and later spectra, and then spectrograms. And this module has given us a lot of ways to narrow down our guesses. We can pick out clues as to the sounds, but even experienced phoneticians, when they're shown a clear spectrogram of a word, struggle to guess exactly what word is being spoken. Our eyes, even phonetically trained expert eyes, just can't pick out the details that our ears have been automatically processing since infancy. And the final section of this chapter takes us through some of the work that's been done to deal with the fact that although two people may be heard as saying the same thing, or even one person in two different situations, we can hear that they're saying the same thing, often the acoustics shows a great deal of variability. So what exactly is it that sounds the same to us? So in this section we learn about concepts like spectral moments and locus equations, and we get a good amount of discussion around the difficulties of this project of finding what's actually invariant, what's actually consistent across multiple different ways that we hear what sounds like the same sound. And that's this chapter. Okay, so just a reminder that the fourth quiz for this course is on Wednesday, March 17th. And this quiz covers material from week 7, which is analysis methods for speech sounds, and week 8, last week's source filter theory. As usual, come along to the tutorial on Tuesday afternoon. That's 5 p.m. Mountain Daylight Time. And I emphasize daylight because Alberta just moved to daylight time. So we set our clocks ahead. So it's now at UTC minus 6 hours. If you're in another time zone that hasn't moved to daylight time this weekend, then the offset is going to be different than it was last week and possibly for the whole term up to now. And so I encourage you, make that adjustment. Use an online time zone calculator if you like. I've linked one in the description for this video. I also want to remind you that the second lab assignment is due next week, Tuesday, March 23rd. All 3 topics, 3 options for that assignment are related to the acoustics we've been doing over the past 4 weeks. Ideally, you've already started on it. We can absolutely discuss any questions you have about that at this week's tutorial, or send me questions by email and whatnot. And that's it for this week's video. I hope to see you at Tuesday's tutorial.